everybody, and welcome back to Digital Integrated Circuits. I'm Professor Adam Teman of the EnICS labs at Bar-Ilan University, and today we'll be going over the first part of the Kahoots for Lecture 10, Arithmetic Circuits. In this Kahoot, we'll be focusing on adders. This Kahoot will have 10 questions, and the first is, what do we call the design approach of the Itanium ALU as shown in the picture here? Is it vector processing? Is it bit-sliced design? Is it register ALU transfer? Or is it tightly coupled ALU? And at least in the context of this lecture, we are of course discussing bit-sliced design. Let's go back and see what that exactly is. And bit-sliced design, shown as part of the Itanium, or in actually pretty much any type of a processor that's kind of complex that you want to implement over here in a kind of efficient way. Well, what we would have is, say, if we have some sort of a processor that has many execution units that are processing in parallel. And we need to actually take our registers and pass them on in many bits. It can be 32 or 64 bits or something like that into each of these functional units that have to apply operations to them. And that's pretty hard to do when we want to take these very wide buses and distribute them over all this type of logic. It creates a mess of routing. So what we should do is kind of take the layout into consideration. And it's really nice if we look at this bit slice type of approach over here. So what we have is we have our registers over here, and we'll set up our bits of our registers. So this is going to be bit 0, 1, etc., until we get to bit n. Could be a 64-bit or something like that. And then we will come over here and drive out the bits on these wires that will go horizontally along the whole AL unit type of unit. And we can then put different units over here, such as one adder, two adders, a shifter, a multiplexer, and different types of things. And then we just have to tap these bits in order to get their inputs and to drive their outputs, and then we'll get the data out, the 64 bits out. So that can make our lines really nicely forwarded together. And you can see that is done over here in this beautiful Itanium type of a layout. And even though the Itanium was not a very successful architecture or a successful product, they did a lot of really cool stuff in designing it. So I just want to say that the problem with this is that in order to do it, we have to have some sort of equivalence between each of the bits. So as you can see, each of the registers for the bits is going to be a certain size and a certain pitch. But then we also want to have our adder, for example, set up where each of the bits is created equally. So we want to be able to design, a single type of a bit slice that is pitch fitted to our registers, and the same thing for our shifters and so forth and so on. And then we can just stack them, and it's very scalable. We can add as many bits as we want if we are able to design, each bit to be equivalent. And that's what we are basically discussing quite a bit in this lecture. Question number 2. How many cycles does it take to calculate an n-bit addition using a serial adder? Here we can see a serial adder type of a thing over here. Will it take us 1 cycle? Will it take us n cycles? Will it take us 2 n cycles? Or it is data dependent? Well, this is going to take us something like n cycles. So let's go back and see what we mean. When we talked about the serial adder concept, at time I, we're going to read AI and BI. Those are 2 bits of the 2 operands that go in, and we're going to produce the sum and the carry for the next input. And for it, we're going to store the carry in an internal state. Okay, so we have a full adder over here, which is going to get bits from each of the operands that are going to be shifted over during each cycle. So the first cycle we're going to take the LSB, then shift it on the next cycle, get the next bit, the next bit, the next bit, until we get to the MSB. And each of these are going to go into these X and Y inputs of the full adder and output a sum and a carry. But we also have to have the carry from the previous bit, from the lower, the lower significant bit over here, that's going to go into the carry in over here. So we're going to use some sort of a register that's going to store that, and during every clock cycle we're going to drive that register out. And that is of course going to take us n cycles to do that. So the answer is going to be n cycles, and I just want to remind you that the reason to do this type of a serial addition is that on really old hardware, every type of transistor or switch or whatever was used was very expensive, and here we can use one single full adder to do this type of a n-bit addition, and so that could be used at a very initial stage of hardware if you have a really simple and low size, small size type of hardware. It's not really going to be done today, but that is the basic concept of how to do this type of an addition on real simple hardware. That's just to question number 3, where what function is calculated by the Cout output of a full adder. So here we see the truth table of a full adder, and is the Cout output doing x plus y plus Cin? Is it doing XOR of x, y, and Cin? Is it doing the majority of x, y, and Cin, or is it doing propagate? And it's really important to look at this full adder. It's one of our main components that we're going to use, and of course the Cout output is the majority of x, y, and Cin. So we're going to go and look back at this full adder, because this full adder is super important. Again, as I said before, it's a simple circuit. It just is this truth table with 3 inputs, which we can call x, y, or a, b, and carry in, or something like that. And it has 2 outputs, the sum and the carry. And really, we can look at it in many different ways. So for one, it's just a truth table. We have 2 functions, s and cout, and they have some sort of bits here, and we can write out what the actual formulas are for this. So S is going to be X, XOR Y, XOR Cin. We can see that over here. So the S, if we have, 2 zeros on X and Y and Cin, we have an even number of zeros or an odd number of zeros, we're going to get a 0 or a 1 in the S output. For carry out, we're going to have, the bits that are 1 for carry out. It's if both X and Y are 1, or both X and Cin are 1, or both Y and Cin are 1. And so that is really easy to look at, that X, Y, and Cin can go in an XOR, and if we want to just use 2 input XORs, we can cascade it through 2 of those, and we'll get our S output, which is an XOR. Or for the carry out, what we want to see here is that we at least need 2 1s in the input, and that is going to be a majority of X, Y, and Cin. So if there are more zeros than 1s, the Cout is going to be 0. If there are more 1s than zeros in these 3 inputs, then it's going to be 1, and that is a majority of these. What is more? Are there more 1s or more zeros in these 3 inputs that we have? That's why we call it a majority circuit, and we can make it like this, with this type of a 2-level representation, as we can see here. So that's one way of looking at it. Another way is looking at it at the kill, generate, and propagate type of way. So when we're going to rippling the carry, which we will see in the next slide, and we discussed often, we want to really see if the output of our full adder is going to give us a carry or not. And it has to wait actually until we get the input, the Cin from the previous stage, to know what the final, sum and carry are of our design. But we can just look at the 2 bits that we have immediately at the start without waiting for the carry, these X and Y, and decide according to them on some sort of a partial type of a formula, which will tell us something about the carry of the next stage. So since the carry is a majority of X, Y, and Cin, we need at least 2 of the input bits to be 1 in order to have carry become a 1. So if X and Y are both 0, as we can see over here in the red area over here, it means that for sure we are not going to have a carry on the output. And therefore, it basically killed the carry. The carry is not going to ripple through this stage of our full adder. So we can call, X bar, Y bar, we can call that kill, as we see over here. On the flip side of that, if both of them are 1, it doesn't matter what the carry that arrives is going to be. For sure we're going to have a carry on the output, because if there are 2 1s, the majority of 1, 1, and either 0 or 1 is going to be 1, of course. So that means we're generating a carry, and we don't have to wait for the carry to ripple through all the previous stages to know if we have a 1. So that is going to be a generate, and that is X, Y. So if both X and Y are 1, we're going to have a generate. The middle condition is going to be called propagate. And the reason is that we have a 1 in either X or Y. So the majority the decision if we have more ones or zeros, is dependent on what this carry in is. If the carry in is 0, then the majority is going to be 0. If the carry in is 1, the majority is going to be 1. So basically, we're propagating the carry in to the carry out. So we're just passing it through. We wait until the carry in arrives, and whatever the carry in is, we send it to the carry out. So that is going to be the propagate, and it is x or y. But since sometimes we don't really care about the accuracy of that, we can write it as x or y, which is simpler to implement in CMOS. So that's kind of another way of looking at this full adder. But another really cool way, actually, of looking at a full adder is as a compressor. So, or as a ones counter, we could call it. There are 3 inputs to the full adder, right? And so there's this input and this input and this input. And what we're basically deciding by the output is how many ones are there. So we're asking how many ones are at the input. And the answer is going to be, C out, 2 to the power of 1 times C out, plus 2 to the power of 0 times S. So this is a binary encoding of the number of ones are over here. If we get 0, 0, 0, for instance, over here, then our answer is going to be 0, 0. There are 0 ones at the input. If we have 1, 1, 1, how many ones are there at the input? There are 3. So that's going to be 1, 1 at the output. Let's say we have 0, 1, 1. There are 2 ones over here. The output's going to have to be 2. So binary encoded, that's 1, 0. Okay, let's take another one. 1, 0, 1. How many ones are there at the input? There are 2 ones, so that's going to be 1, 0. 1, 0, 0. There's only one 1 at the input, so the output's going to be 0, 1. So C out S is just a binary encoding of how many bits there are at the input. And since we have 3 inputs and we encode it into 2 outputs, this is a type of a compression. We take 3 inputs and propagate it out to 2 outputs. We often call such a thing a population counter, okay, or a pop count. So this is another important function that we need to use often in different things. It's become especially very, very prominent in things like binary neural networks that have become popular lately. A population counter is asking how many ones do we have in a vector, in an n-bit vector. And this is, for a 3-bit vector, a full adder is a population counter, or a 3-to-2 compressor, or all kinds of things. So the full adder is this really important tool that we have to do all kinds of things in binary arithmetic. Of course, the answer for what the C out is majority of X, Y, and C in, but we discussed a lot more about it. Question number 4. What is the propagation delay of an n-bit ripple carry adder? So here we have a little ripple, and is the propagation delay going to be n cycles? Is it going to be O of n squared, or O of n log n? So of course the answer in this case is going to be O of n. Ripple carry adder, as we can see over here, is just this type of a structure that cascades several of these full adders. So this is going from right to left. Okay, and here we have it going from left to right, but we have these full adders that are cascaded to each other. And what we're doing on a schematic kind of a way is that we're taking, the LSB over here, which in this case is A1 and B1, we're adding them together. That will produce us the first sum, and then we take the carry and we'll send it over, or ripple it over, to the second full adder, which is taking the inputs A2 and B2 of the 2 operands, but adding them along with the Cin, counting the number of ones over here, putting out the sum and the carry and so forth. So that's a ripple carry adder, or looking at it with a better view using full adders and using A0 and B0, and the Cin 0 is going to be 0, but we're just going to take out the sum of that, the carry of that, bring in C0 0 with A1, B1, and we're going to get the sum of that and the carry, and we're going to get, keep on rippling until we get to the final sum and the final carry. And the problem here is that we take, this addition and provide this carry. Only after this carry arrives can we go and provide this carry and this sum. And only after this arrives can we provide this carry and this sum. And only after that, this carry arrives, can we provide this carry and this sum. So really, our path is going to go through, first carry propagation, second carry propagation, third carry propagation, and either fourth carry propagation or some propagation. And that means it's going to be, some sort of an O of n. If we have n bits, it's going to take, n stages in order to calculate that. And therefore, it's a really slow type of addition, but it ripples the carry through our whole line. Okay, so the answer, of course, is O of n. And it leads us to the next question, which is, how is the mirror adder approach able to reduce the logical effort of a ripple carry adder? So the question is, the answers are by sizing all the transistors equally, by removing redundant paths to the output, by using half adders to implement the entire circuit, or by exploiting the inversion property. And of course, in this case, the answer is going to be by exploiting the inversion property. And I'll go back to that and explain. So our problem over here is that when we want to create logical effort and we have all these stages, we have, logical effort is going to upsize everything by about fan out of 4 or something like that. So if we have n stages, we're going to have 4 to the power of n or something like that, size increase. And that does not work well with our bit slice design. Remember, well, not only with our bit slice design, in general, if we have 64 bits, that's going to be 4 to the power of 64 or something like that. So we're looking for all kinds of ways of reducing this logical effort and eventually bringing it into a bit slice design. And we showed in the lecture a cool way of really employing logical effort in a very application-specific way, where we know that the carry is the only important critical path and the sum isn't, and therefore we can size everything really to make it with the same sizes and fit in the bit slice. But even before that, just taking a standard mirror adder, and I just wanted to discuss this because it's a pretty cool idea and I really like it a lot. If we redraw our full adder to really to benefit the carry versus the sum, we can get, this type of a strange structure where we also see that we can remove some transistors and arrive at this interesting thing which isn't basic CMOS, because what we have here is that the pull-ups and the pull-downs are equivalent. We have, these two PMOSs in parallel connected to a PMOS in serial, and the same thing we can have for our pull-down network with NMOSs, and the same over here, and the same over here, and the same over here. And that is not standard CMOS. Usually we have, an NOR network on one side and an AND network on the other side, or something like that. But here it actually happens with this full adder, and that benefits that we have, we pull out the carry computation really early, and then we can get the sum, which is not on our critical path, a bit later. So what happens is, though, when we get this type of a thing, it's really interesting, because if we look at it and we put A, B, and C into our full adder, we get C out and S, of course. But if we would just invert the inputs and take A inverted, B inverted, and C inverted, we would get C out inverted and sum inverted. And that's called an inversion property. And how can we exploit it? Well, the problem is that with logical effort, we need this inverter in order to provide us with this carry in that is non-inverted. And since we have the inversion property, we can actually remove that guy and just take, C out inverted over here and drive it to the next stage. So we take our first stage, which is getting A0, B0, and C in 0, and what we know is that we're going to, get this point over here is going to be C out inverted. Okay, so if we take C out inverted over here and put it into the full adder, but add it along with A inverted and B inverted, okay, so we put an inverter over here on A and on B, and we know that we took the C out from over here rather than from over here, then it's also inverted, and therefore we're going to get sum inverted, so we can just add another inverter over here to get sum 1, and we get carry out inverted. But since carry out inverted comes over here, we take this, which is carry out non-inverted. So we already get carry out non-inverted. And that is good for inputting along with A and B non-inverted, which gives us sum non-inverted. And since we take it over here again, we're going to get the carry out over here inverted. And again, we can continue along like this. So we can keep on skipping this inverter and reduce one of the stages for in our logical effort for each of the bits. And so we get the logical effort divided by 2. It's still a huge logical effort, and therefore we continued on and showed how we can really reduce the logical effort to get a equivalent stage for each bit slice and fit it in our nicely equivalent sized bit slice design, which is kind of something that we can do in a real design. So the answer is that by exploiting the inversion property, the mirror adder approach reduces the logical effort of a ripple carry adder. Question number 6, what is shown in the following picture? And we have this circuit over here, okay? Is that a carry look-ahead adder? Is it a Manchester carry chain adder? Is it a Brent-Kung adder? Or is it a dynamic mirror adder? Well, I'm going to go for a Manchester carry chain adder. Let's see that. So this is a Manchester carry chain adder, and it's a really fast type of a cool adder. So we can take this circuit over here, which is really ingenious and very cool. If we take this guy over here and we say the carry out, remember, it gets to be 0 for sure if kill is 1. So if both A and B, or X and Y, are 0, then we know that carry out is 0. So we can take that kill, which is again A bar, B bar, or something like that, right? And it's immediately available. We don't have to wait for a carry in order to get that. And we can connect it to this NMOS, and it will pull down the carry out and provide 0. On the other hand, we have the generate. Generate is AB, but we'll take the generate bar. And if we have A and B are both 1, that means we can, with the bar, we'll get a 0 over here, and then we can pull up the output because that's creating a generate. But if we don't have, a generate or a kill, that means that A and B are going to be a propagate over here. So we can put the propagate as the input to a pass gate, and then we'll propagate the carry into the carry out. As we said, all we want to do with propagate is take the carry in and pass it along to carry out. And we can do that with either a static circuit over here or with a dynamic circuit to get fewer transistors over here. And we can put it in, cascade it. So we take the carry in, we put, the pass transistor over here that propagates carry in to carry out, and just take several of these stages, 1, 2, 3, 4, and we can really propagate over the carry into the carry out, or stop the propagation if we got a generate or a kill or something like that. Okay, so this is going to be our Manchester carry chain, and it's really, really fast. Can we put this, 32 of these in series? And the answer is probably not, because remember that each of these pass gates, if it's one like this or one like this, they add serial resistance, and we get this, large increase in propagation delay due to the serial resistance. So every once in a while, what we're going to do is we're going to take, finite sizes of this, such as, 4 of these together, and buffer them. Buffer the carry after that. Okay, but that's a really cool way of doing this, a Manchester carry chain, and you can make a very fast type of an adder in that way. Our next question is, what is the worst case propagation delay of a 32-bit carry skip adder with 8-bit sections? Is it going to be about 4 gate delays, about 8 gate delays, about 10 gate delays, or about 32 gate delays? And again, we have a 32-bit carry skip adder. We're going to have 8-bit sections in there. And the answer is going to be about 10 gate delays. So let's understand why. A carry skip or a carry bypass adder is this really cool idea of how to reduce the propagation delay through an adder. So if we have a general adder, ripple carry adder as shown up here, we saw already that the problem is that we have to really carry through the whole thing to get our worst case. So our worst case is going to be if really each of these full adders has a propagate coming into them, and we have to run the carry through until the end, and we're going to have a propagation delay of whatever it takes to calculate this propagate, right? The propagate is a function only of x and y, only of a and b. We have to calculate that, and assuming it's propagate, we have to take the carry in and send it through here, and then this is going to be propagate as well, so we have to send it through here. This is going to be propagate as well, send it through here, and so forth. So we get this long delay of the carry, which is going to be something like, you know, three propagate delays, three carry delays plus the propagate calculation delay. But the cool thing is here that we don't necessarily need to do this for all of our 32 or 64 or whatever bits. What we can do is say, if we knew that we're going to propagate the carry from the input to the output, why don't we just put a mux over here on the end and say, listen, if we wanted to propagate all the way through, then let's not go through all these full adders, let's just skip it, let's bypass it, and go through to the end. So we can take, some sort of a selector on the mux that says, okay, if propagate 0, 1, 2, and 3 are all, 1, we have propagates through all of these, then select this and just bypass the carry. Does that help us? The answer is it does not. It does not help us on if we want to go through all n bits, because probably just to calculate this whole thing would take something on the order of the n bits. But if we do it on a small section, then this calculation can be highly reduced. And then our worst case is just going to be, the propagation through this small section, or or else we're going to carry it. And why is that nice? Because we can do, since these guys are just a function of the propagate and generate, which are available, at the beginning, they don't have to wait for the ripple of the carry through the whole circuit, then we can do that in parallel with further on down sections. So if we look at the design over here, what we can see here is we do this setup. That's, calculating the propagates and the generates, these guys over here, and including the selector of this mux over here. And we can input bit 0 to 3, bit 4 to 7, bit 8 to 11, bit 12 to 15. So this setup is calculated in parallel between all of them. The delay of this T setup is done over all of these at the same time. Okay, so that means that if we had a generate or a kill somewhere over here within these sections, we're going to already be able to pay for the propagation over here, and then we're also going to be able to select it. It'll go through this, and we don't have to wait for the whole carry to propagate through. But during this calculation over here, we're also going to decide if we want to take the other stage. So then we would carry through here. Okay, and again, the same thing over here. Once we would arrive at the output over here, we already know if we're selected on this input or this input. If we're on this input, then we don't have to go through all of this. We just go through right over here. We just go right through here. Just go right through over here. And we really save this whole thing. So what we're going to have over here basically is we're just going to calculate the time that it's going to take us to calculate the propagate or the generate. The worst case is if it's going to go through 3 out of these 4 stages. So that's n over m minus 1 over here times the t carry. But then, and then it's going to go through m minus 1 of these bypasses, and finally figure out the final sum. So that's the whole thing, and the big part over here is the n minus m, so we get an O of n minus m. And we can see that, as long as n is bigger, so we have, ripple carry adder is going to linearly increase at a pretty high gradient over here, whereas a bypass adder may have some overhead just for a really short ends. The addition of this multiplexer and so forth is some overhead. But once we cross something like 4 to 8 stages, really the bypass adder is going to be faster than the ripple carry adder because the gradient is going to be lower. It's going to be n over m instead of O of n. So that's a really cool way of doing such a thing. Okay, and so that leads us basically to our next question over here, where we're going to have a puzzle. And we're going to organize the adders from the fastest at the top to the slowest at the bottom. And we have the mirror adder, the square root carry select adder, the carry bypass adder, and the carry look ahead adder. And we want to put the fastest at the top and the slowest at the bottom. And we pretty much already saw over here that the mirror adder is really the slowest of all of those. Then we have the carry bypass, which we saw over here. And we're going to see in a minute that this square root carry select is a bit faster than the carry bypass. At the top we have the carry look ahead adder, which is the fastest adder we know how to make. So let's go back to our slides and look at its square root carry select. So carry select adder is very similar to a carry bypass adder, except it uses a different operation. So a carry select, not a square root carry select, all it does is it figures just as before. Well, in the carry bypass, we calculated, you know, if everything in a certain section is going to be a propagate, and then we just decided to propagate the carry. Here we do something very similar. We calculate what if the carry in was a 0 or the carry in was a 1. So we have these two you know, pieces of hardware. One is calculating if carry in was 0, we would get some solution, and it takes TPD to figure out what the carry is. And if carry in was 1, we figure out it takes TPD to select that. So that, again, we don't have to wait for the carry to provide this, you know, this and this, because we assumed that the carry was 0 here and the carry was 1 over here. Now all we have to do is drive the answer to that and the answer to that into a multiplexer, and according to the carry in that gets there, select which one it is. So what we need to do is we need to figure out the propagate, you know, the PGK, right? The PG type of thing, propagator generate, and then we need to put the P and G into these two units. One of them selects, you know, it decides if we had a carry of 0, the other one assumes that we had a carry of 1, and then we take the multiplexer. So, you know, our first critical path is going to be through this whole section over here. But this is done in parallel to the second one and the third one. They all happen at the same time. So basically, when the carry comes out of the first stage over here, it gets to the second stage, and we're already waiting. We know what the answer is over here and the answer is over here. So we just have to decide on if we take this direction or this direction. So it's just the propagation delay of a multiplexer, and so forth and so on, just the propagation delay of the multiplexer. So again, in that type of a way, we parallelize the computation on what we have ready at the beginning, the propagate and generate, and then just wait for the multiplexer. And the basic you know, type of propagation delay of that is very simple to the carry bypass adder that we saw before. But what we can do, and this is true for carry select and it's true for carry bypass, we are doing these, you know, setup calculations kind of in parallel. And it takes a while for the first one to propagate through, and it takes a while for that to propagate through the multiplexer and so forth. So we can actually do this type of a thing, which is dependent on the number of bits that we're using. We can do it on fewer bits than what we do on the second one, which has a bit more time. So as you see here we took 2 bits, here we took 3 bits, here we took 4 bits, and here we took 5 bits. And because it's going to take a while until this gets over here, we have more time to do this, you know, setup type of an action over here. And that provides us with the square root of 2n type of a propagation, which is really nice. And we can see that if the ripple carry adder had this high gradient linear increase over here, and we had the linear select, which is the carry the carry select or the carry bypass had a smaller gradient. With the square root carry select, we get even a better gradient over here of and if we have a large adder, we get better propagation delay through it. So that's another kind of a cool thing. Finally, we have the carry look ahead adder, which we'll show in a few minutes, which really gives us a logarithmic type of an improvement in timing. Our second to last question is, what is the best case propagation delay of a tree adder, a carry look ahead adder? Okay, so here we have a logarithmic rule, and you can understand what the answer is going to be. Is it O of n, O of log of n, O of n log n, or O of n squared? And again, the logarithmic rule, what I said a minute ago, is, you know, hinting to us that the answer is O of log n. Usually when we're going to be saying log, we mean log 2. When we talk about binary stuff, we're talking about log 2 usually. So that's really going to be the approach. So let's remember what a carry look ahead adder is, or what a tree adder is in general. And a tree really provides us a logarithmic reduction. It depends on the radix of the tree, but with a radix 2, we're going to have a log 2 type of a reduction. So I'm going to remind you how a carry look ahead adder works. And just over here we have, you know, the formulas for generate and propagate. And we saw that carry out, so again, generate and propagate are just functions of A and B. So they don't have to wait for a carry to be calculated. But carry out can be shown as the generate, okay, because if generate is 1, then we don't have to wait for the carry out of the previous stage, plus propagate, because propagate is saying, we just pass on what was before, the carry in of the stage before. So that's what carry out is. Carry out is either we have a generate, or we propagate the carry in, and that is our carry out. Okay, so we can go and make this recursively and show and do it and apply it onto sets of propagates and generates. So if we define something that's going to be propagate 1 to 0, and we say that is propagate 1 times propagate 0, and generate 1 to 0 is going to be generate 1 plus propagate 1 times generate 0, so that's what we have over here. Okay. What we can do then is say that C out of 1 is generate 1 to 0 plus propagate 1 to 0 times C in 0, which is very similar to what we have here. It's just kind of grouping the propagates and the generates of 2 bits. Okay, and that we defined as carry out 1. The same thing we can do with any 2 groups of bits. So propagate 3 to 2 is going to be propagate 3 times propagate 2. Generate 3 to 2 is going to be generate 3 plus propagate 3 times generate 2. And carry out of 3 is going to be generate 3 to 2 plus propagate of 3 to 2 times C in of 2. Okay, so we grouped together basically a bunch of pairs of bits just to make this kind of radix 2 propagate and generate definition. Now we can go and do the same thing over again, where we take these groups of 2 and group them as well. So propagate 3 to 0, which will be from this guy to this guy, is going to be propagate 3 to 2 times propagate 1 to 0. Generate 3 to 0 is going to be generate 3 to 2 plus propagate 3 to 2 times generate 3 to 0, 1 to 0. And the carry out of the end of this whole group of 4 bits is going to be generate 3 to 0 plus propagate 3 to 0 times C into 0. And we can keep on doing this until we get, P of n to n minus 1 to 0. And so such a tree with a radix 2 is going to have some sort of O of log 2 of n. We can see that in this type of a way over here. So we took groups of 2 bits and we put them into a propagate generate type of a thing that's going to do, provide these types of computations. The outputs of 2 of them are going to go into another one, so that's basically making, these guys over here, that's this propagate generate unit, and so on until we finally get the propagate generate of n minus 1 to 0 and of n minus 1 to 0. And that's really going to give us, the C out of n minus 1 to 0, and it's going to be logarithmically fewer stages than going and rippling the carry all along the way. That is not necessarily enough, because we also need to get internal values and so forth to calculate everything, as we're going to see on the next question. So the answer, of course, is O of log 2 of n. So our final question over here is going to ask us about what is the radix of the Kogge-Stone tree shown in the picture. And so we have this Kogge-Stone tree over here, and we see that we have all these different groups of A's and B's in a 16-bit adder, and we see what they do. They go all over the place over here. And so the radix of this thing, if you count over here, you see that each one of these guys is, it goes to 4 things, or each one of these dots over here gets 4 inputs to it. So the radix of this guy over here is going to be radix of 4. Okay, so let's see what that means. Okay, so these are the trees, and these different trees that are going from, I guess you could say, maybe one extreme to another, they have several names. So a Brent-Kung tree is on the left over here, and a Kogge-Stone tree is on the right over here. And what Kogge-Stone is doing, if we saw before we have these propagate 1 to 0 and then propagate 3 to 2, Kogge-Stone is actually providing us gates for doing, propagate from we had propagate 1 to 0 before, and we had propagate 3 to 2, so it's also adding us this internal one of propagate 2 to 1. Once we have all of these guys, we can figure out what the sum of 0 is, what the sum of 1 is, what the sum of 2 is, and what the carry of 0 is, the carry of 1, and the carry of 2, in order to get each and every one of the bits very simply. So as you see here, in this case we have a radix 2, which means that the input of each of these gates is just going to be 2 bits. So we take A0, B0 and put them into a propagate generate type of a unit over here. We take A1 and A2 and put them in another one. We take A2 and A3, put them in another one. So we made all of these combinations. And since we did that, we are able to then take the output of that and we can combine them into, another bunch of these. Okay, as you can see over here, and get this next grouping of each and every one of them. And we need, in order to then go over and find each of our sums, which is what we want in the end, we need 4 stages on this case where we have 16 bits and radix 2. In other words, we have these propagate generate units of 2 inputs. So these are going to have a radix of 2, as we saw before. This Kogge-Stone tree is a radix 2 Kogge-Stone tree, and it's going to have a tree depth of 4. But at the worst case, we have to go through 4 of these dots, 4 of these propagate generate units, in order to get the sum of any one of our output bits. On the other hand, we could have done this in a more sparse way because we needed a lot of hardware to do this. So a Brent-Kung tree is just showing the opposite. And there we take, A0, B0, and A1, B1, and we make our propagate generate unit. Then we have a non-overlap, so A2, B2, and A3, B3. We have our second propagate generate unit, so we don't make this internal one. And then the outputs of those guys, we make this, P3 to 0 and G3 to 0, but we don't have the internal ones. And therefore, if we want to get, for example, sum 2, we have to take the output of this, and we have to take this input and use another gate over there to figure out what sum 2 is over here. And therefore, what this causes is that, as you see, we have a lot less hardware. We have many fewer of these propagate generate gates, but we have to add these internal gates as well. And then if we want to get, for instance, sum 14, we may have to go through 1 propagate generate, 2 propagate generate, then this other gate, this other gate, and this other gate. We needed like a tree depth of 5 in order to arrive at that. Yes, in order to arrive at our S15, we only needed 4 gates, just as in this case over here. But if we wanted to arrive at S14, we needed 5 gates. So our tree depth got larger and our critical path got longer because of that. Okay, so this is a kind of a trade-off between having, a Kogge-Stone tree, which has a lot of hardware, but the worst case, we're always going to have, this minimum tree depth, versus a much more sparse tree, such as Brent-Kung, where we're going to have much less hardware in order to do it. But in some cases, for some of the sums, we're going to have a longer propagation delay in order to find, the final answer. So this is a trade-off that we have to do, and therefore we have all these options that we had before. If we go back to our drawing over here, what we have over here is each of these gates is going to get, 4 inputs from it, so that's why it's radix 4. And due to being radix 4, we're only going to have to really go through 2 stages in order to solve this 16-bit input tree, whereas here we had to go through 4 stages. It's just because the fan-in of each of these propagate generate gates is bigger. And this is another trade-off. How long does it take us to calculate this propagate generate when we have radix 2 versus radix 4, as opposed to the number of stages we need to pass in order to get our solution? So these are the different trade-offs in circuit design of these types of adders over here we have. So that was the end of this Kahoot, and please continue into the second part, which is 10b, about multipliers. And of course, as usual, you are always welcome to ask me questions on my YouTube channel, and I'll try to answer them.